Okay, so this week we're going to continue on algorithms and algorithm analysis. That'll probably take us up through the rest of the week, meaning that we've got about 3 weeks left, and so in those 3 weeks we'll be looking at tree-based data structures as well as a review towards the end. And I do want to note that a lot of the stuff that we're covering from algorithm analysis through up to the end is on the final homework, which is all written. So there's nothing that you will submit through the web grader to no code or anything like that. Instead, it's all written. And so I would encourage you that you don't put that off to the end either. As we're covering this, take a look at that last homework and understand the tools that you need to retain in order to do that last homework. And since it doesn't require any programming, you can work along on that last homework along with your the remainder of your programming assignments. Last time we started talking about algorithms and algorithm analysis, and I gave you some motivating examples, and we ended with this 5-step process that I described for analyzing an algorithm. One is that you identify the input, and if you've written good pseudocode, then that's already taken care of, right? Writing good pseudocode already identifies the input. The key there, though, is sometimes there might be more than one input. So there might be, the first example we're going to do here today is linear search, where you've got a collection of elements and also a key element. Which one is most appropriate to look at? Probably the collection, because that's what you're going to be iterating over. Then you identify the input size, and even then you have to be careful, because there are some things that are pretty straightforward. If you're iterating over a collection, then it's the size of the collection. If you're taking an image and you're changing every single pixel, then it's the dimensions, n times m, or width times height, or however you want to look at it, the total number of pixels. But on the other hand, the thing that we looked at the last time was, what if it's just one number, right? If it's a number like n and you're trying to determine whether or not n is prime, then you have to be careful there, because the way that you represent a number is by writing it down. So in other words, the size when you write it down is the number of digits. Or from the perspective of a computer, it's the number of bits required to represent that number. So at the end of the day, a number, when you represent a number, say an integer here, then it's the number of bits. Oops, I went into LaTeX mode there. It's the number of bits needed to represent x. In other words, log base 2 of x. And that's so common in computer science that we think in binary all the time in computer science. We simply just write it as log of x. So when you don't have a basis, an explicit base pointed out for you, then usually we mean base 2, right? Now, if you were in calculus or some math class, they'd probably mean the natural base, because that's at the point, because that's the base at which the first derivative doesn't change it, right? There's no constant sitting out front. But because we work in binary, right, then we like base 2, and so that's our default base system, okay? The third, oops, sorry, let me go up here again. The third step here is to identify the elementary operation. And so that's where we'll pick it up today here. So what is an elementary operation? Basically, the motivation here is that to characterize on algorithms complexity, you need to capture a notion of how much work it does, right? And so that's why you want to identify what operations are actually going on with this algorithm. Because if you look at a sorting algorithm, then there's no pixels there at all. So operating on a pixel, that's irrelevant when you look at an algorithm over here that's sorting a bunch of numbers, and vice versa, right? Changing an RGB value to sepia tone, right? That has nothing to do with sorting a bunch of integers. So it's entirely up to whichever algorithm you're looking at that point. To simplify the process, you whittle it down basically to one operation. You identify one operation with which to analyze the algorithm, right? An algorithm can be doing many things. It can be doing a bunch of additions, maybe a bunch of subtractions, maybe a bunch of divisions, a bunch of comparisons. It's got a for loop, so you're doing I++. You're iterating over a list. Maybe you're doing linked list stuff, and so you're going from one node to the next node to the next node, right? There are lots of operations potentially that you could look at. So which one, it gets way too unwieldy to look at an algorithm and analyze it with respect to 10 different operations. So instead, you try to whittle it down to one single operation. And that usually is, in general, you select the most relevant, or the most common, or the most expensive operation. Right? And by expensive, I don't know what I mean by that, because again, it's entirely up to the algorithm that you're looking at, right? And it's also, from an engineering perspective, there might be some situations in which the engineering concerns start to take over, and it doesn't matter whether or not this operation over here is more common. This operation over here is way more expensive. The quintessential example I can give you is that generally we've got Garmin comes in every year. They have yet to visit this year. They'll be or I think that they might already have. But Garmin comes in, and every so often this engineer from Garmin will describe how they had a panel. Garmin makes a lot of stuff for avionics, right? Aviation stuff. And so one thing that one of their products was searching for the closest airport in case you needed to land or something like that, or do an emergency landing. And so of course that means sorting. And you could do a quick sorting algorithm like quick sort or merge sort that we'll take a look at, revisit those things later on. Or you could do a slow algorithm. I think they did either bubble sort or shell sort or something like that. It's a much slower algorithm. Why did they go with the much slower algorithm? Because they had different engineering concerns. That slow sorting algorithm, yeah, it was slow with respect to comparisons. It did a lot more comparisons, but it was more optimal for the way that they were for their embedded system, the way that it was actually storing stuff. It was a lot less memory intensive, and so that was their bottleneck, right? That the memory accesses or shuffling of the around of memory was way more expensive on that embedded system than was a comparison. So they chose this sorting algorithm over here, which is traditionally slower, over the more quicker sorting algorithm because of one comparison over here was actually quicker than over there. So those are engineering concerns, and I can't tell you what's more expensive in general because it's always going to be, there are some generalities that you can come up with, but it's always going to be an engineering concern. All right? So let's look at some examples. For example, if you were searching or sorting something, then you could look, as I said before, comparisons. Right? If you could do arithmetic operations, like additions or subtractions, or division or multiplications, or divisions. Right? So why did I put slashes there? Why might an addition be kind of similar or almost exactly like a subtraction? X plus A. They're the inverse operations of each other, right? X minus A is nothing more than X plus negative A, right? So they're basically the same operations on modern computing devices. What about multiplications and divisions? Why are they the same? Exactly. Division is just multiplication of the reciprocal. A divided by B is nothing more than A times 1 over B. And there are lots of numerical tricks that you can do to get the reciprocal, 1 over B, right? So those basically are the same thing. Now, which one, among additions and subtractions and multiplications and divisions, which one of those is more expensive on hardware, say? Definitely multiplications and divisions, right? Additions and subtractions, those are pretty straightforward. In fact, you can have a constant depth circuit do it for you with a look-ahead adder, basically, and you might be doing that in, say, 230 or 231 eventually, right? But those are some other operations. What are some other operations that we've seen already? Say node traversals, right? That costs us, and in terms of the motivating demonstration that I gave you last week, when you are doing something naively with a linked list, then that becomes your bottleneck. That becomes so expensive that it would take you 20 years to compute the sum naively of a linked list of elements in a linked list of even 1 billion elements or something. Whereas it would only take you seconds or mere minutes if you did it right, or if you did an array-based list instead. Okay? Again, it all depends entirely on the algorithm that you're looking at. So to remind ourselves, that's step 1, 2, and 3. Right? Let me go back up here. The elementary operation. Once you've identified the elementary operation, and by the way, there can be multiple correct answers there. Right? A sorting algorithm does swaps. A sorting algorithm also does comparisons. A sorting algorithm may also do something else. Right? It accesses memory or something like that. And each one of those might be the correct way of analyzing it with respect to the actual problem that you're trying to solve at the time. So there might be multiple correct answers giving you different characterizations of the algorithm. That's perfectly fine. Right? Again, we identify the input size, the elementary operation. And finally, number 4 is we determine how many times the elementary operation is executed with respect to the input size. In other words, you come up with a function. And it doesn't have to be t sub n. I chose t sub n because t time, right? In general, it just can be f of n. If you've identified this elementary operation and it cost you 1 unit, right? It cost you 1 unit of time. Maybe that's a microsecond, maybe that's a minute, maybe that's a year, right? Maybe it's just $1, right? If you want to think of it that way. Just think of it as 1 unit of resources. And that's your elementary operation. Now, how many units do you actually end up having to pay to sort a list of n elements or something, right? That's step 4. And usually it means coming up with a summation. Usually it means looking at the algorithm line by line and saying that this line is executed this many times, and then that's nested inside a larger control structure, and that control structure is executed this many times, and so you come up with some summation, some formula that gives you the number of elementary operations with respect to n, right? So that's what we're going to do today. I'll go ahead and cut and paste this and go through it again. You analyze how many times the elementary operation is executed with respect to the input side. I wanted to avoid this right here. You want to produce a resource function, f of n, which is a mapping. We may not have a lot of discrete math yet, but it's a mapping from the natural numbers onto the positive reals. Why is it the natural numbers? 0, 1, 2, 3, 4. Have you ever heard of an input size that's negative? Can you have an input size that's negative? Input into a computer, you certainly is 0, right? No input at all. But can you put in a negatively sized input into a computer? Does that make much sense? No. Likewise, can you have 3.5 inputs? What does that mean? Right? If you have a set or if you have a collection that you're trying to sort and it has 5 elements, 6 elements, 7 elements, that makes sense. But can you have an array or a collection of 3.5 elements? No. So we're going to restrict our attention here on the domain to the natural numbers, and the codomain, the thing that it maps to, positive reals. Why not? I mean, you could include 0 in that if you really wanted to, but why positive reals? Again, we're measuring a resource. This costs you something. Have you ever heard of a computer that when you run it, it pays you? I have. What am I thinking of? Get a bunch of 1080Ts, start running stuff, and yeah, you're paying for power, but if somebody else is paying the power bill, then what can you mine? Bitcoin, right? So you can run stuff that pays you in some sense, but that's not real, right? Somebody's footing the bill for that electricity, right? If you can get somebody else to foot that bill and then you mine the Bitcoin for yourself, all the better, right? But as far as a theoretical point of view from looking at resource measures, there's no such thing as a negative resource. There's no such thing as an algorithm that pays you or takes a negative amount of resources to actually compute, right? It'd be like going back in time. If I start my algorithm today, then my result ended up being computed 10 days ago. It doesn't make much sense, right? So it might require a collection of summations, as I said, maybe finding a closed form solution of them. It might require a deeper analysis. Eventually, we're going to look, revisit quicksort, merge sort, and binary search, which are all have a recursive nature. How do you analyze those recursive algorithms? And the tool that I'll give you is just simply the master theorem. Okay. In general, you want a worst case analysis. In other words, you don't. We'll look at an example here that typifies this, but Some algorithms can be very, very quick depending on if they get lucky. Some algorithms might you might have an average case analysis in which how many operations does this algorithm actually execute on average? Generally, though, you want to prefer a worst case analysis because you can't always be optimistic and assume that the algorithm will get lucky and immediately execute. But maybe you don't want to be a pessimist either, but that gives you the most realistic point of view. What is the absolute maximum time that this algorithm will take? Right? That's what we're really interested in. So the examples that I want to do here, and I'm going to switch over to the overhead projector here, are two algorithms that you've seen before, hopefully, from CS1, linear search and selection sort. We'll write the pseudocode together to get get more practice with pseudocode, but hopefully you're familiar with them already. Linear search is just given a collection, say an array, and a key. Start at the beginning, search through until you find something that matches the key. Right? So here's an array of integers. Does it contain 5? Yes or no? Well, you start, if it's not sorted, then you have to start at the beginning. Is this 5? No. Is this 5? No. Is this 5? All the way to the end until you say, no, there is no key like that. Or, yeah, I found it right there. There it is. Right? So let's go back to the .cam here. Right? And I watched the video the other day when I did this, and unfortunately, yeah, this is... I wish that I could like tighten this up or something like that, but it does. I'll try to leave my hands off the table as much as possible here, so that it doesn't jiggle too much. But remember linear search, right? And remember when writing pseudocode, the two things that you do immediately are you identify the input and the output. So what's the input with linear search? If I were doing this in C, it would be an int star array, and then an int size of that array, and then an int k for a key, right? This is not C. If this were Java, it'd be different. I wouldn't have the size of an array. I wouldn't have a pointer. I would just have int bracket array, and then int k for a key, right? So I don't want either one of those languages. I want pseudocode. Right? So it's going to be a collection of elements, and I'll give that collection a name, implying immediately that there are n elements in here and that it's indexed on 1, right? Like math does rather than CS does, because this is more general. Again, a collection of elements. Did I specify that it was integers? No. Did I specify that it was doubles? No. But I do need a key K. And we'll output an element, X, in A, such that X is equal to K. Now, I didn't say equals equals. This is not a dynamic programming language, so equals equals equals, strict equality testing. I'm using the mathematical notation, and I also didn't mean I didn't say what X or what K is or what any of these elements are. What does it mean to be equal? That's entirely up to you. It doesn't matter. That's a detail left for an actual implementation. If this were a bunch of integers, then I would use equals equals. If this were JavaScript and I wanted to do strict equality testing, I would use 3 equal signs. If this were Java and I was comparing students, is this student equal to this student? I would probably want a comparator instead. Right? So there we go. That's good enough for now. Let's go ahead and say for each a sub I in A. I'll go ahead, again, I get into the habit of writing those colons. I don't mean to do that. That's very Pythonic. Python, right? For each element A, if A sub I is equal to the key element, right? And I do like parentheses there. It makes it a little bit neater. Then what do? I found an element that matches the key. So I'll output. I don't return, remember, because it's not a function. I output X. Or, sorry, A sub I is what I called it here. There. Basic linear search. In fact, these 3 lines could be translated into pretty much any piece of code, right? Just a basic for loop, comparison inside of that, and then a return statement instead of an output statement. Except, what other case am I missing here? If I gave you an array of 5 elements, 1, 2, 3, 4, 5, and I asked whether or not 52 was in it, you would answer, no. Are we taking care of that kind of situation here? Nope. So, if I don't find what I'm looking for, what do I output? What would you do in, say, C? If I were to design this linear search to give me the index at which the key exists, what would be and so the return type is an integer. What would be a flag value telling you that doesn't exist? -1 or something negative, right? If this were Java and I had big I integers and I wanted to know the index, maybe what else could you do instead? You could return null, a special flag value. You could throw an exception. Element does not exist, right? You could do all those things. What do I do here, though, in pseudocode? Well, I'm not going to do null or -1 or something like that. I'm going to do phi. Right? And so I'll be explicit about that up here. Phi if no such element exists. All right? Yeah, it's as focused as it's going to get, unfortunately. There we go. Okay. There's our linear search algorithm. Anybody who's taken a CS1 course could define this in whatever language they're familiar with, right? Of course, you wouldn't. Why? You would use some built-in library function to do it for you, right? So let's go through our 5-step process. Note that we have not covered step 5 yet. We're saving that in order to get more practice on steps 1 through 4 before we get there. So step 1, what's the input? Well, it's already identified up here, but as we've said before, there are some cases, and this one being one of them, where there might be 2 answers, A and K. Right? So let's simplify it by only going with one. Which one is most appropriate here? Probably the collection. A. 2. What's the input size? And again, if we've written good pseudocode, this is already taken care of for us as well. What's the size of A? N, right? I was explicit about that. N. 3. What's the elementary operation? For this, I like to go back and 1, 2, 3, 4. Number your lines, right? So that you can say, well, it's that thing on line 5 or whatever, right? So what's the what are some operations that are going on here, by the way? What's the most obvious operation that's going on? Probably the comparison there, right? Is this thing equal to that thing? But there's also some other operations here, right? For each. Well, you have to have some iteration. So if this collection were a linked list, then you would be iterating on each node. So maybe node traversal is happening up here on line 1. If this were a for loop, just a traditional for int I equals 0, I is less than n, I plus plus, right? Then you're doing a comparison there as well. You're doing an initialization, a comparison to see if you're done with the loop, and an iteration, an addition, I plus plus, to go on to the next element, right? So there's an addition, there's a comparison on line 1, there's a comparison on line 2, right? Which one is the most appropriate, though? Okay, the comparison on line 2. Let's go with the others that I was talking about there for a second here. If this were, say that this is a traditional for loop where you're going for I equals 0, right? That's an initialization, but it's only ever done once, right? Whereas this one is done for as many times as you iterate over that loop. So 1 versus multiple, probably multiple. Let's go ahead and eliminate that one initialization. Then for I equals 0, I is less than n. Well, that's a comparison too, right? So, but that comparison is done just as many times as this comparison is done. So if you really want to add those up, fine. I've got one comparison here, one comparison here. So one iteration of this entire loop results in two comparisons. But the iteration of the loop itself is, say we go all the way to the end. This is a preview of step 4. And we do n of them. Now I've got two n comparisons. Ultimately, at the end of the day, when I get to step 5, do we care about those constants sitting out front? No. So I'm going to go ahead and just go with 1 here so I don't have to have a constant sitting out front within my analysis. And finally, you go I++. That's an addition. All right? So you're doing one addition versus one multiplication. Generally, you look at things that are nested inside of loops. Also, the initialization int I is equal to 0. The continuation I is less than n. And the increment I++. Those things are necessary for the control structure of the algorithm. This is just a control structure right here on line 1. The real work of the algorithm is done inside that loop. And that's where we should focus our attention. We generally don't look at things that are necessary for the control structure of the algorithm because they're going to be proportional. Say that I did a full analysis of every single operation. I'm doing 2n comparisons, I'm doing n additions, I'm doing 1 initialization, right? Or update, n of those if you really want to be technical about it, right? In other words, I've got 2n plus n plus 1. Does that change the nature of that? That's still a linear function, right? So it's going to be proportional no matter what. So I'm going to focus instead on the comparison on line 2 here. For how many times or how many comparisons are made is the comparison on line 2 executed with respect, WRT, with respect to the input size. That is n, right? Because that's what we identified up here on step 2. All right? So this is where it can depend, right? Let's be very, very optimistic here. What's the fastest time that this could run? Just one comparison, right? You get lucky. Say that there's 10, 20, 30, 40, 50, and you're searching for 10. Guess what? It's at the very first one. At which point you say, oh, I made one comparison, I'm done, right? So you could say, under an optimistic point of view, the best case scenario is that it's going to be one comparison, right? Under that, you find x at the first element. All right? That's one way of looking at it. Is that the most sensible way of looking at it? Always assume the best case scenario? No. So what's another way of looking at it? Okay, the average case. Now, this goes beyond this course, but if you want to, you can look at it. I think I maybe have written it up in the textbook. The way that you would actually want to do this is to define a probability distribution on a successful search on each one of the indices. Then you assume the worst case scenario of your probability distribution, which is going to be a uniform probability distribution. You add all these things up, and you get an answer. That answer looks something like. We'll come back and fill in that later, right? So best case scenario, or not best. That's up there. What's the worst case? It takes all the time. What does that mean? So you have to you go through everything that you're searching for, and what happens? Where do you find your keys? At the last place that you looked for them, right? Because then you found them, right? So you look for there are 5 elements. No, that's not it. That's not it. That's not it. That's not it. Oh, you get unlucky. It's the very last one, or it results in an unsuccessful search. So. Worst case scenario, how many comparisons did I end up making there? Make n comparisons, which is going to be when you find x or k, these are keys, right? K at the last element, or an unsuccessful search, right? So like I said, you're going to, the proper way of doing the average case scenario would be to define a probability distribution, sum those up, define a probability of an unsuccessful search, blah, 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 and come up with basically something that looks very much like the naive way of looking at it of, if I just have the average case scenario here, I've got the worst case here, I've got the best case here. Naively, what could you do? Best case plus worst case, and then you take their average divided by 2, which is essentially n divided by 2, right? Or, again, another way of looking at it is 1/2 n. So, from a practical point of view, an average case complexity analysis is very, very enticing, right? And for certain algorithms, like we'll eventually look at heap sort, an average case or an amortized average case analysis is definitely the one that you want to go with because it gives you the most real-world behavior of your algorithms. Definitely it's most real-world here, but does it matter? At least in this scenario. 1/2 n versus n. Characterize this function. This is a linear function, right? Gee, I wonder where we get the name, right? This is a linear function. What is this? It's still a linear function. So from the point of view of the complexity of the algorithm, it doesn't make a difference whether or not you look at the average case or the worst case. You definitely don't want to look at the best case because then you get the misimpression that this algorithm is a constant time running algorithm. But instead, linear, it doesn't matter. We're ultimately going to ignore these constants sitting out front here, right? But this is our final answer, right? Just n is good enough. Step 5, which we haven't gotten to yet to describe, I'm going to go ahead and put in order n, right? Because, again, I want to ignore these constants. This is big O analysis, and we'll talk about that, and we'll give a full definition by the end of today. What I wanted to do next, though, was look at another algorithm that hopefully you're familiar with, selection sort. Okay? Again, the input is going to be a collection. A equals A1 through AN. And our output will be A sorted. So we'll just be making changes to it. We're not making a copy and sorting the copy and returning a pointer to the copy. We're not dumping it to a linked list to an array-based list so that we can sort it faster or whatever. All right, it's just pseudocode. Don't worry about that stuff. Now, remind me, how does selection sort work? Here's a bunch of elements. You go through and what do? You find I want to put something at the beginning of the list. I want to put something that belongs at the beginning of the list. So if I've got this huge list of this collection, what do I need to find if I want to put it at the beginning? The smallest value, the minimal or minimum if they're all unique, right? So I'm going to iterate through it, find the minimum value, select it, and then put it at the beginning of the list. That leaves me a list of size n-1, the remaining elements, because this guy is where he needs to be. So n-1 elements, I go through, find the next smallest element, and where do I put it? At index 2. Right? And I keep doing that, and keep doing that until the list gets smaller, 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 smaller. And what about that last one? So if I've sorted n-1 of them, and I select this one and then put it where? Where it needs to be? Do I need that last iteration? No, it's do nothing. It's select. If I only gave you a list of size 1, would you bother sorting it? It's sorted by definition. Right? So we're going to write pseudocode to do that. Okay. For I running from something up to something, what we're going to do is, and you can put comments into your pseudocode. I just tend to go with C-style comments. We'll find the minimum element among elements I through n. Right? Remember, we're indexing on n here. So what we run I for, we're going to have to come back and figure that out. So I'll go ahead and keep track of the min element here. So if I'm searching from a sub I through a sub n, where do I start? Well, a sub I. Assume that that's the smallest one that you've found so far. Then go through with the rest of them for j running from I plus 1 up to n, and make a comparison. Is the jth element smaller than the minimum element that you found so far? So if a sub j is less than the minimum element so you found so far, then I will update the minimum element, a sub j. There we go. At the end of that inner for loop, I've found the minimum element. Where does it need to be? At index. It needs to be in the front of this sublist here, so it needs to be at the front, so I need to put it at index I. So to do that, indexing, do you have random access? I don't know. I don't care. Swap a min and a sub I. If you were to actually write this in code, you'd have to come up maybe with a temporary variable. Int t is equal to a sub I, then a sub I is equal to min, then min is equal to t, right? You have 3 lines of code instead of 1 line of pseudocode here, using plain old English. And, well, this one is index-based. I don't know, maybe I should have been keeping track of the min index. If you were to program it, yes. This is just pseudocode. You get the idea of how it works, okay? Now, where do I begin and where do I stop, right? So where should I start sorting this list right here, or this collection, sorry? I should start it at 1. And as we already said, do we need that last iteration? Nope. So I'll go up to if I've sorted the first n minus 1 of them, then this thing is where it needs to be. So there's no point in being there, in looking at it and deciding I'm going to swap it with itself, right? That's what you would end up doing, okay? There's great pseudocode for selection sort. Now we need to go through our 5-step process. I'll start up here. 1, the input, again, good pseudocode, that's done for you, is the collection A. 2, input size. Good pseudocode, it's going to be n, okay? 3, what's the elementary operation here? So I'll go back and 1, 2. I do like numbering comments because then you can refer to the comment, right? The comment on line 2. If you didn't do that, if you didn't number your comment lines, then you wouldn't be able to do something like that, right? So it's 7 lines of code here, or 7 lines of pseudocode. What elementary operation do we want to pay attention to here? There are a couple of correct answers, right, that will give you different analyses. For example, swapping. That might be expensive on your system. I don't know if it's true anymore, but it used to be that flash drives, for example, reading off of a flash drive didn't really negligibly impacted the lifespan of flash drives. Writing to them, though, right? You could only do, say, 1,000 writes, but you could do 1 million or 1 billion reads from a flash drive. Same with CDs, maybe CDRs and CD rewritables. Every time you rewrite a bit on there, it degrades a little bit. So you can't rewrite it infinitely. But you can read it pretty much without degrading the medium itself. So maybe your engineering concern is we need to pay attention to these swaps because memory accesses are way more expensive or degrade our hardware way faster than anything else that the processor does. So you could look at swaps. Would it be appropriate to look at these for loops running initialization of I is less than equal to n minus 1, I plus plus? Those are necessary for the control structure of the algorithm. So probably not lines 1, definitely not line 2, it's a comment. This is done once for each one, but we're doing something after that with a for loop. Whatever we're doing here is way more common than this iteration right here. So that gets us down to these 2 lines. Right? Probably want to focus on what? That comparison right there. So the comparison, comp, on line, 5? Right? Determining whether or not the thing that you're looking at right now is smaller than the thing that you found so far. Right? because eventually you're going to swap them down here. So 4, how many times is the comparison on line 5 executed with respect to n? So for that, I'm going to go ahead and go into a split screen here, best I can. Okay, it's hiding it. So I want to focus on the innermost execution. That's nested inside of a for loop. That's nested inside another for loop. So let's just go ahead and focus on line 5 here. If I only looked at line 5, how many times am I doing a comparison? If I only look at line 5, how many comparisons do you see there? 1. Right? So there's 1 comparison on line 5. Right? Now if I expand my scope out, right, to the innermost for loop here, then I ask the question, well, how many times is line 5 executed with respect to the loop on line 4? Right? So you might immediately come up with an answer of, well, it starts at I plus 1 and goes up to n, so that's what? Oh no. I plus 1, I plus 2, I plus 3, I plus 4, ... all the way up to n would be, well, how many did you skip? If you started at, say, 1 and went up to I, you skipped all those, right? And so 1 up to I is going to be, right, if I go 1, 1, 2, 3, ... up to I, and then I plus 1, and then ... up to n, right? I skipped all of these. How many are there? I, right? How many are there total? N. So if they're a total of n and I skip I of them, how many are left over here? N minus I, right? Right? But I'm not going to do it in that fashion. I'm not going to immediately jump to that answer right there. That's what it will be. But I'm going to set up a summation instead. A summation that starts j at I plus 1 and runs up to n. Because you're adding 1 comparison, 2 comparisons, 3 comparisons, 4 comparisons for each time that you iterate over this while loop, running j from I plus 1 up to n. Right? So this would be 1 plus 1 plus 1 plus 1, ... Oops, I should have started over here, for n minus I times. Right? That expands out to, what line is that? Line 4. Okay? Now the question becomes, well, how many times is the block on line 4 executed with respect to the for loop on line 1? Right? Well, again, another summation. I equals 1 up to n minus 1, and then this entire thing is in parentheses here. Otherwise, leaving off the parentheses is the same thing. Okay? So that expands out to line 1. And there's no other expansion because it's not nested in anything else. Okay? Now we need to get a hold on this value right here. For that, I'll go ahead and go back over here, repeat the summation. I is equal to 1 up to n. Summation of j equals I plus 1 up to n. Oh, sorry, n minus 1 over here. And then we're summing up 1s. Now we need to solve this summation. Again, you're skipping I. You're going 1 plus 1 plus 1 plus 1 all the way up to n. That would be n total in general, but you're skipping I of them. So that inner summation is going to be n minus I. Don't lose your outer summation. Okay? Now, what can you do with this, the summation? A plus b, or the summation of sums is equal to the sum of summations. You've heard that before? Or it's just like the limit of, in calc, the limit of, what is it? How does it go? The summation of limits is equal to the limit of summations, right? You can split them up. Well, this is a summation. It's n plus negative I. So you can split this up into 2 summations. I running from 1 up to n minus 1 of n, minus, and I'm just taking the negation out front here, I equals 1 up to negative 1 of I. Right? All I'm doing is splitting up this summation. If this were multiplication, I couldn't do that because the limit of multiplications is not equal to the multiplication of limits. But in this case, it's a summation, so I can split those sums up. All right? The first one's super easy. This is n plus n plus n plus n. How many times do I do that? Goes from I up to 1 up to n minus 1. So 1, 2, 3, 4, all the way up to n minus 1. So it's just simply n times n minus 1. Okay? This thing should look familiar. Where have we seen something like this before? This thing is 1 plus 2 plus 3 plus ... And then we only end at n minus 1. That showed up before, right? Where did we see that? When we were doing the naive painter's way of doing the linked lists, right? We started at the beginning and then went, we wanted the ith element. So we started at the beginning, traversed all the way to I. Now we want the I plus 1th element. So we started at the beginning again and traversed all the way to I plus 1. And we came up with a summation that looks something like this, if I thought I did that. But if I didn't, then, well, what does this look like? There's a famous name that came up with the closed form solution of something like this. Also, what's another name for a normal distribution? You know, Gauss, right? Gauss. I don't know, it depends on if you're German or not. This is Gauss's formula. That if you've got a summation of I running from 1 up to n, in other words, summation of natural numbers, 1 plus 2 plus 3 plus 4, ... it's n times n plus 1 all over 2. That's the classic first example of proof by induction, right? And the story goes, that Gauss was bothering his tutor or whatever, so his tutor said, Go write down the numbers 1 up to 100 and add them all up, thinking that he could get rid of them for an hour or so. And he immediately thinks about it and says 5,050. Why? Well, he derived this formula in his head, plugged in 100 times 101 divided by 2. Well, that means that this is 50 times 101, so it's 50/50. Right? And so he came up with that formula. I don't know if it's true or not, but supposedly he came up with the formula when he was young. Now, I don't have all the way up to n here. I have n minus 1. So when I plug n minus 1 here and n minus 1 here, then the minus 1 plus 1, they cancel out, and I got n times n minus 1 all over 2. The second one is half over the first. So when I subtract it, I get n times n minus 1 all over 2. Now, if I expand this out, what's the most important term here? N squared 1/2 minus 1/2 n. What's the most important term? N squared. And so step 5, which we'll get to now in a moment, is going to be order n squared. Right? Ignore lower order terms, ignore constants, and you get what's called big O analysis. Okay? All right, let's switch over to that. There we go. Come on. Okay. So those are the two examples. We'll come back to more examples later on, in particular with other sorting algorithms. But here's our motivation for big O analysis. This is step 5 of that 5-step process. So hopefully we have a pretty good grasp on those 4 easy steps, or 4 simple. The analysis, that might require some practice, but those first 3 certainly are the easiest. You just identify things. But the motivation is ultimately we want to characterize our algorithm for larger and larger inputs. The whole reason that we build faster and faster hardware is so that we can process more and more data. And in other words, more and more data means that your input sizes are going to grow. You go from, say, handling 1 million integers in 1970, and whoa, that's impressive, to handling 10 billion integers in a few seconds here in 2019. Next year, if you handle, desktop, not next year, but another 20 years, maybe a desktop computer can handle 50 petabytes or something like that, right? That's the growth factor there. Right? In other words, as you look throughout history, the larger and larger data means that n is approaching infinity. It's not. I mean, it's growing, right? It's not ever going to approach infinity because there is no such thing. But it's growing and growing and growing, becoming larger, approaching infinity. Right? That's our motivation. We want to ignore small input sizes. For small input sizes, the practical differences may not matter much at all. And you saw this in practice. When I did that motivating example with the linked list versus the array-based list, and we only had, say, 1,000 elements, this one was immediate, this one was immediate. If you only kept your worldview at a small amount of data, everything looks the same because everything is so fast, right? But when you start, and in fact, let's look at that again. There we go. There was the actual graph that we put together, that I put together. All right. If you only keep your world very, very small down here, then the differences between the array-based list, which is basically just the x-axis here, and the linked list implementation here, for anything up to 100,000 integers, there's not that much of a perceivable difference. But when you get out to, say, 1 billion integers, or this is 1 million integers, I don't remember. I don't remember what the scale on this is. But when you get out here, the differences become huge. And that's what we want to capture there, right? And so for small input sizes, we really don't care. There's not that much difference at all. In fact, some algorithms may even give a misimpression that they are faster, but only for small input sizes. And when we look at, we'll see an example of this when we revisit merge sort. Merge sort is very fast because it has this divide and conquer kind of strategy. But it turns out that merge sort is actually slow for sorting small collections. Sorting collections, say, of 20 elements or less. Because you're paying for the recursion with merge sort, quick sort, whatever else you're doing. And so the recursive nature of that algorithm, it doesn't really pay when you've got a small array of size 20 or something. Then going with selection sort, or a better sorting algorithm that I'll show you, insertion sort, that's much better. Right? And then you can design hybrid algorithms that if the input size is large, then go with this algorithm. Until the input size becomes small enough, then switch over to that algorithm. Right? And you can do practical implementations like that. That's how Java did it up until Java 7. Right? It switched off to insertion sort. So they could get the wrong impression. In fact, here's a graph. This is just a made-up graph here. Hopefully it shows. There we go. That I did on Wolfram Alpha at some point. And suppose that I've got two algorithms, the blue algorithm and the red algorithm, or the magenta algorithm, or whatever you want to call it. And I measured their performance like I did with the linked list and the array-based list. And I compared them, right? And these are the graphs that came out of that. On the x-axis, you've got the input size. So as the input size grows and grows and grows, of course, the amount of resources is also growing, right? The red one is characterized by n cubed, if you can't read that. The blue one is characterized by 50n squared plus 50n, right? So it's quadratic, and the other one is cubic. But if you only look at input sizes of 100 or less, right? If I restrict my attention to everything from 100 or less, then which algorithm looks better from the graph? Remember, this is measuring resources, so fewer resources are better than more resources, right? Because less cost, higher cost. So if I only focus on input sizes 0 up to 100, then which algorithm gives you the appearance that it's better? The n cubed algorithm. But at some point, these algorithms' performance crosses over. And if you look at I can't expand it, but if you look at the trend line all the way to infinity, will the blue one will the blue one ever go above the red one again? Never. The blue one will always stay from 101 and on. the blue one will always stay below the red one, meaning that for input sizes of 100 or more, the blue algorithm, the algorithm characterized by the blue, is going to be way better. Right? So if we don't care about low input sizes, small input sizes, we only care about its trend as it tends towards infinity, then we need a tool to characterize that. Right? Let's see. I'll go ahead and cut and paste this so it's in the notes, but it's everything I just said. For small input sizes, the red function is better, but for large input sizes, the blue function is better. So in addition, we need a way to ignore hidden constants, ignore lower order terms, because we want to scope down our characterization of an algorithm to one function, and one function only. We don't want 50 out in front because, improve the hardware, and that 50 goes down to 25 in practice. Right? So to characterize these algorithms, we need big O analysis. Right? And the O stands for Omicron, but and I'm not up on my Greek, it's Greek. But I've been told that there's no difference between a Greek letter Omicron and a regular old English character O. So we just say big O analysis instead of big Omicron analysis because it sounds weird maybe, I don't know. Right? So I need to give you this definition. Now this definition is going to be a little bit different than what you might see in calculus or analysis or wherever else this is used. This goes back way before modern computers. It characterizes functions and the limit of functions and stuff like that. But here's our definition that we're going to use. Let f of n and g of n be functions. We say that f of n is big O of g of n. Hopefully this is rendering fine. Okay, yep, good. Of g of n if there is a positive constant c and an integer n naught such that f of n is less than or equal to c g sub n. Right? And we're going to look at a couple of intuitive ways of looking at this. But the quick snapshot of this is if I've got this f and I've got this g, f is asymptotically less than g, right? Less than or equal to g. All right? And a couple ways that you can look at this is that at some point, this function will always be less than or equal to this function when you take some constant and stick it out front. Okay? In other words, it's a way to characterize growth. Right? Big O characterizes a function's order of growth, right? As n tends towards infinity. Right, there we go. So as your function grows, or as your input grows, right? Then how do your functions grow? A linear function grows linearly. A quadratic function grows quadratically. An exponential function grows exponentially, right? And how do you know those things? If you, what's another way of characterizing the growth rate of a function? Think calc, for those of you in calc. If I take a function and I want to know what's the change in the rate of change, that's how they put it. Take the first derivative, right? So if I take a linear function and I take the first derivative, n, what's the first derivative of n? 1. In other words, it has a constant rate of growth, right? What if I take a quadratic function, n squared, and I take the first derivative? What do I get? 2n. The rate of growth is linear. Right? What if I take an exponential function, e sub x, or e sub n, and I take the first derivative of that? What's the growth rate of an exponential function? What's the first derivative of e sub x? E sub x. In other words, the rate of growth is still exponential. What's the rate of growth of the rate of the growth? What's the second derivative? Same thing, right? It's still exponential. And that's why exponential functions are huge. You don't want to deal with those. Right? If you have an algorithm that runs exponentially, no, terrible. Don't even think about running it. Right? Okay, so basically it gives you a way to characterize the function's order of growth. It allows you to ignore lower order terms. It allows you to ignore constants, right? And both of those together, it allows you to focus on the most significant term in a function, right? The largest growing term, or the fastest growing, I should say, fastest. There we go. Right. So here's our notation. Right. In this class, we'll go ahead and use the following. We write f of n is equal to big O of g sub n. And again, that O is omicron, but there's no difference, so you can just write it as O. If you look at other asymptotic analysis, and I've got those in the pre-prepared videos there, and you might look at them in, say, 235, where we assume that you do have calculus, that we kind of assume that you're going through calculus in this course. But those are all defined in terms of limits. And they have an equivalent definition with respect to limits. But you've got big theta notation, you've got big O notation like we have here, and you've got big omega notation, you've got little omega notation, little theta, or there's no little theta, little O notation and stuff like that. We won't get into that. That's our notation for this course. The correct notation, or you can use the correct notation, which is going to be in O of g of n. All right, there we go. So I don't assume that you have set theory here, but if you do, then you can use that notation there, and you might see that correct notation. The second one is correct notation because the thing on the right-hand side is actually a set of functions. So if you say that this function is in this set of functions, then that means something. But if you take the first notation, it kind of tells the same story, but equality means something different. This function is equal to this function. A big O of this function, it doesn't make any sense. The thing on the left-hand side is a function. The thing on the right-hand side is a set of functions. So they're incompatible. We can't say that this thing is equal to that thing. But for this course, it's perfectly fine to use that notation. You see that all over the place, even in textbooks. It's an abusive notation, but it's a common abuse of a notation. So it's kind of like using poor grammar, right? I can't think of an example off the top of my head, but sometimes using poor grammar. Oh, you don't want to do that. Oh, I forget what it's called, but using he or instead of him, or using as a preposition, or using she instead of her, or to her instead of to she, right? If you use correct grammar, you're always going to be correct, but you realize that you can break the rules sometimes, right? And here's one instance in mathematics where it's fine to break the rules, right? Okay, so the definition is not tight, right? For example, here the following are all true. I can say that n is or big O of n, but also, what else is it big O of? N is big O of n squared. Right? Also, another thing that you can write is n is big O of n cubed. Right? Those are all true. It's not tight. Remember, in the definition, it's less than or equal to. So all three of these things are true because the growth rate of n is less than or equal to the growth rate of n. In fact, they're equal. It's less than or equal to the growth rate of n squared. It's also less than or equal to the growth rate of n cubed, right? So all three of those things are true. It's a loose comparison because of that less than or equal to. If you want a strict comparison, that's big theta analysis, where you say that the growth rate of this function is equal to the growth rate of this function. Right? We're not going to go there, though. Okay? So the immediate question is proofs. Right? How do you prove given f of n and g of n, how do you prove, I'll emphasize that f of n is big O of g of n? There we go. there are a couple ways that you can do it. In fact, there are 3 ways that you can do this, and if you watch the videos or if you read the textbook, you'll get all 3. I'm going to show you 2, and then highly encourage you to use 1 because it's way easier. The third way of doing it is using limits, setting up limits, maybe applying L'Hopital's law, maybe applying a bunch of other stuff. If you've got calculus and you're comfortable with limits, yay, go ahead and do that. Again, we don't assume calculus here, so I'm going to show you 2 other ways. The first approach, basically, the answer is you have to show an inequality. You have to show an inequality, right? And so there are going to be 2 approaches that you can do to this. Approach 1 is given 2 functions, you can find their crossover point, okay? Let me go ahead and go back to this graph up here. And that's basically what we did when we looked at, oh, well, at 100 or thereabouts, I don't know what that is, but it's actually 101. After that point, these 2 functions are monotone increasing, and they will never, ever meet again, right? And that's one way of showing that this function is always greater than or equal to this function, and so you can show that it's big O, right? Another way of doing it is, in other words, mathematically what you do is you fix C to be 1, and then you find that crossover point. You find that n naught, that after this point, this function is always greater than this function right here. Another way that you can do it, approach B, is that given 2 functions, you find an inequality that works for some n naught. Let me cut and paste there. An inequality that works for some n naught. That is, you fix n naught, and then you find C. You take these functions, you set up an inequality, and you say that this function is bigger than this function. Make it bigger, make it bigger, make it bigger, but not too big, and then you've shown an inequality. I'm going to show you both of those right now with respect to these 2 up here. All right? So let me go ahead and switch over to the .cam. Okay. All right. So the first step here is to identify our intuition. We've got n squared plus, what was it again? 50n squared plus 50n versus n cubed. Your intuition on which one of these has a higher rate of growth already. This is quadratic. This is cubic. So we want to show what? We want to show that 50n squared plus 50n is big O of n cubed. Right? Because n cubed has the higher rate of growth than n squared. Again, if you could just chop off lower order constants, chop off the constants sitting out front, n squared is big O of n cubed because n squared grows only linearly if you take the first derivative. This one grows, the rate of growth here is quadratic if you take the first derivative. Right? So this is what we want to show. And our approach A is to, what was it again? Fix, which one was which? Yeah, fix C to be 1 and then find the crossover point. All right. In other words, I want to show this. F of n is less than or equal to C sub n for all n greater than or equal to g of n for all n greater than or equal to n naught. But if I'm fixing C, what happens here? What happens to C if I fix it to be 1? Goes away. It simplifies it. I have 2 unknowns here, n naught and C naught and C. Right? And if I've only got two equations, 2 unknowns, then well, you got to fix one to find the other. Right? So I've thrown out C basically. Now I only have 1 unknown. I want to show that this inequality holds for all n greater than or equal to some n naught. And from the graph, that looked like it was 101. How do I go about proving that? Right? Let me go ahead and change the inequality to an equality. 50n squared plus 50n is equal to n cubed. Right? Now I'm going to take everything and collect it onto one side. Right? N cubed minus 50n squared plus 50, oops, that should be a 50, right? 50n is equal to 0. Right? I've changed the problem. If I have a polynomial and I set it equal to 0, and I want to know the values of n that satisfy this, what am I doing? If this were just quadratic, what would you be doing? You would be applying the quadratic formula, and what does the quadratic formula give you? Negative b plus minus square root of 4ac, b squared minus 4ac all over 2a gives you what? Those give you roots. Right? That's what it means to set an equation to 0 and then find the roots. Find the values of x, or in this case n, that satisfy this equality. In other words, that give you the roots where it crosses the x-axis. Right? Well, I don't have a quadratic equation here, do I? This is a 50, sorry. What do I have here? Cubic equation. So does anybody know the cubic formula instead of the quadratic formula? There's actually 2 or 3 cases. There is one, but I don't know it either. So I want to simplify this, which is why I didn't put any constants down here, like plus c. N, n, and n. What can I do? I can factor out an n. One of those roots is 0. All right? When I do that, that gives me a new equation. N squared minus 50n plus 50 is equal to 0. Now what is that? That's a quadratic formula, or a quadratic equation, quadratic polynomial. And now what can I apply? The regular old quadratic formula. Remind me what it is again? Negative b, so that would be plus 50, plus minus square root of 4a, 1, c, so that's, oh, sorry, b squared would be what? 50 squared is what? 2,500, right? And minus 4ac would be 4 times a, that's 4 times c, so that would be 200. Help me out here. Arithmetic's not, up on a stage, arithmetic's hard, right? And all over 2a, so that's just 2. Pull out your calculators. Anybody have it? What are my roots here? I think one of my roots is going to be 100.49, and the other one is negative 100.49. In other words, n squared and n cubed, they cross over and meet in 3 different places. Right? One of the places that they meet is 0. And if you go back to that the graph that I showed you before, right? They meet at 0. Right? Another place that they meet is positive 149. Another place that they meet that was not graphed was negative 149.49. Does this one matter? We don't care about the negative domain because there's no such thing as a negative input. So, who cares? Now, 0 versus 100.49. Which one of those do we care about? We care about the rightmost one, the largest one. Right? So after this n, then f of n is less than or equal to g of n, where c is dismissed here. So in other words, what's my n naught? Conclusion. For c equals 1 and n naught being 100.49, this one has to be an integer. That's all right. What's the next integer larger than 100.49? 101. F of n is less than or equal to c, g of n, for all n naught greater than or equal to, or for all n, sorry, greater than or equal, 101 you said, 101. Right? And that's, my proof is right here, because I was able to find those roots. Right? Now, with only 1 minute left, we're not going to be able to do approach B until next time. But why the approach B is what I'm going to suggest that you do as a matter of course. Why? Let me go ahead and give you another 50n to the 5th plus 8n 4th plus 7n 3 plus 2.4 n squared plus n plus 130 or 1,037, right? Versus, I want to show that this is order. Well, what is it? Obviously order. If I ignore all the lower order terms, ignore the constants, then what is it going to be? N to the fifth, right? How jazzed would you be about finding the roots of a degree 5 polynomial? You want to? No, I'd throw it into a solver first before I even try to. So this is why I'm going to suggest that you go with approach.